Hi there. I hope you are doing great, you all. So today we are going to start a new subchapter. So this chapter is about homogeneous, linear, high-order, constant coefficient differential equation. As you can see, like it is like homogeneous, linear, high-order, constant coefficient differential equation. Because as we can see here, just see, okay, here we have a constant coefficient a, okay, a raised to n, and so on and on. And then we have high order differential, how can I say? It is linear, okay, let me just define by this term. So first we have, this is homogeneous. Why it's homogeneous? Because it is all equal to zero, okay? So this is homogeneous, the definition of homogeneous function or equation. So secondly, so we have there, it is linear. Why is it linear? So as you can see, it is in a form of a line, okay? So what else? What else? It's higher degree, okay, higher degree, because here the degree is greater than 1. What mean the degree? Degree is this one, n is the degree of this guy. So what else do we have to explain this one? So yeah, constant coefficient. Here you have a. This a is a coefficient. Sometimes this is a is x. So for this case or for those case, that will be not, that cannot be considered as a constant coefficient differential equation. Okay. So in this case, this is constant coefficient differential equation because all the coefficient here attached to this the differentiation term, okay, are numbers or are constants. Okay. Nice. Whenever we see an equation in this way, okay, in this way, in which we have higher degree, n, okay, n greater than 1, and what else? Higher degree, constant coefficient, all the terms attached to this differential part are numbers, okay, or are constant, and what else? And it is equal to 0. So 0, as you can see there, okay, 0 is equal to 0. Then we can say this is homogeneous, linear, because it's in a form of a line. So linear, homogeneous, linear, high order, constant coefficient differential equation. Now, sometimes we have expression like this, okay? Sometimes we have like x square dy square by dx plus, okay, x. Then we have like a 2x time dy by dx, then plus y equal to 0. So this expression cannot be considered as a constant coefficient differential equation. And we have a different way to approach this kind of solution or to this kind of equations. Okay? Now we are just dealing with constant coefficient differential equation. Okay? When these guys are all constant. Okay? Constant coefficient. So the point is, for this constant coefficient differential equation, we will solve pattern and we are going to have we are going to settle a kind of general solution for this one. So that, let us just start. See, we all know that to have the solution, suppose, okay, suppose we have an equation like this, okay, let us see, y dash, y double dash, like y second order derivative, okay, plus, then here we have, suppose we have 5 or it can be 6 y dash plus, okay, plus, then here I have something like 5 y is equal to 0, okay. How to solve this kind of equation? That's the point. See, I will solve for each of those equations, okay, for each of these equations, okay, one case per day, okay, because for homogeneous linear high order constant coefficient differential equation, what we have to understand is, okay, there are some particular case that we are going to solve. First, when it is like when it is an equation like this, okay, in this case, okay, then we are going to solve uh, like in the second form. Suppose we have this one, okay, this is differential equation. Suppose we have this, and it is plus 6y dash and plus 9y equal to 0. Okay, how to solve this equation? Okay, from this equation, I will take the general, how can I say, the general term or the general solution of this kind of equation. Okay, I will call this equation. The way I will solve this one, I will call this case 1. Okay, because from this, I will infer, I will, how can I say, I will extract the general solution for all of this kind of, how can I say, all of this kind of exercise. Okay, I will call this case 1. And I'll call this case 2. Okay, so here it cannot be, it may be maybe like it is 2 and it is only 1, that like this. Okay, now let us break up for this one. Let us solve for this one first. Okay, so first you have to be sure that this one is a constant coefficient higher order differential equation, and it is. Okay, higher order, because here I have I have 2 times. Okay, the order of the differential equation is 2. Here it is 2 also. I'm just solving for 2. Okay, for higher order with the degree 2, and you can solve for degree 3. We can solve for degree 4, degree 5, and so on. But I will start for degree 2 so that you can have the idea, the most important idea. Okay. Then when it comes for degree 3, degree 4, degree 5, it will be easier to you to solve this kind of equation. Okay, now let us start for this case 1. Suppose we have here, this is for our case 1. So here we have y dash plus 6y dash plus 5y is equal to 0. Now see, how to solve this equation. The first thing you have to do, okay, before start solving is, see, here we have y dash and this guy. So we apply, okay, I'm solving to find the general solution that you usually do. So you apply y is equal to Euler raised to, you can say like Euler raised to v, okay, where v is a constant, whatever constant. I'll put v because I like v, okay, V-numerical. So v, okay, and let us say that this y here is a function of x, okay? Y is a function of x, okay? This is like dy by dx is equal to y dash, okay? So y is a function of x. So you can just make a change, okay? I will just do this one, okay? F of x is equal to y. So here y is a function of x. So I will substitute y equal to Euler raised to v times x, where this v here, it can be v, it can be d, whatever you feel like. So where this v is a constant and x is the independent variable, okay? The variable that is independent with respect to y. Now see, what do we have to do? So the next step is just to find, we now know what is y, so what should be y dash, what should be y double dash? So y dash will be this expression, apply derivative. If I derive this expression, this will be only v Euler raised to vx. Okay? Now, if I found this one, y dash, now I'm going to find y double dash. So y double dash will be equal to what? Just check it. So y double dash will be this expression derived. I know this v is a constant, okay? So this one will go down again. It will be v squared Euler vx. Okay? Nice? Now that you are done with this one, what you're going to do, you will substitute all of this expression in this main equation. Okay? Substitute all of this expression in this main equation. So what will be this one? So what you are going to have, that's the point. If you substitute all of this one here, just check here. This one, okay, y double dash is equal to v squared Euler raised to vx. So this will be, in the place of this one, this will be v squared Euler, okay, Euler vx. Okay? Okay. This one is been placing because of this. And this one will be plus 6. And then I will substitute this one, this expression here, y dash. Y dash is v Euler vx. Then plus 5. 5 what? Y. What is y? Y is Euler raised to vx. Vx. And it's equal to 0. Now, this expression here, as you can see, if we take common this Euler raised to vx, what will we going to have? Euler raised to Vx, okay? It will be V squared plus 6V plus 5, and it's equal to 0. Now see, this expression here, this equation here, we know that to be equal to 0, this one must be equal to 0, and this one must be equal to 0. Okay? So what you have to do then? See, it will be impossible to make this Euler raised to Vx equal to 0. So we have to find what is the value of V, okay, so that we can substitute in this equation, and this will be equal to 0, because this one we cannot get a solution. But if we find the value of V and substitute here, then we will substitute this Euler raised to Vx in the main equation. This Euler raised to V, the value of V that we find here, we will substitute here, and we will put where? We will put this value, okay, in the main equation, so that we can see if this value, or if this expression is a solution for this differential equation. Okay, so now check this. Now check what we are going to have. We are going to have only V squared plus 6V plus 5 equal to 0, because this one is impossible to make it 0. Now we are going to find this V here. We find V here. So after finding V here, we will substitute for this expression, and we will substitute in the main differential equation, so that we can see if it is truly a root for this differential equation. See, V squared and CV plus 5. Everyone know that here it is the sum of the roots, and here it is, it is the sum of the roots, and here it is the product of the roots. So we know that it will be V plus 1, okay, and V plus 5. This is equal to 0. Now that we found here V will be equal to minus 1, and V will be equal to minus 5. Okay? These are the two values for V. Sorry, let me put something like this. Okay. These are the two values for V, right? So we found the two values for V. V is equal to minus 1, and V is equal to minus 5. What should we write here? So it means that we will substitute for V, okay? So we will substitute for V, okay? Euler, in this equation, this expression here, we will substitute where you have V, okay? Euler raised to Vx, okay? And here, Euler raised to Vx. Just substitute, put this one, put here. What you are going to have? Minus x. And here, put this one there. You are going to have minus 5x. Okay? Minus 5x. Minus x, minus Euler to raised to x, and minus 5x, right? So these are the solution for this expression directly. If we substitute this Euler raised to minus x, we pick this one and substitute it here, okay, and substitute it here and put it here, and we put this one here also. Just put this one, Euler, for V equal to minus 1, put this Euler raised to minus x in there, and here and here. Just complete the sum. You are going to get 0, and you will see that this one is solution for this differential equation. Okay, so this one will be solution for this differential equation, and this one will be the same. Okay, just try and you will see. Now that we know it is our CF, we all know that for homogeneous differential equation, okay, for homogeneous differential equation, we have only one solution, like the implicit, how can I say, the particular integral for this homogeneous linear high order constant coefficient differential equation, okay, the particular integral is 0. Why particular integral is 0? Because every high order differential equation, okay, has a general solution, something like, okay, the general solution for homogeneous, or for high order differential equation, non-homogeneous, homogeneous, the general solution is CF plus PI, as we know, okay? But this CF is the solution that you get solving only this part over here, okay? The solution we get. This is complementary function. We got the solution of this part over here. It is what we call CF, complementary solution. But the next, okay, the other member, like here it is 0, right? So if here it is 0, so particular integration is 0. But if it were something like, suppose here I have a function of x, okay, then I should go for this particular solution. But here I don't have, and we will see this in the next video maybe, okay? So it means that for this case, for homogeneous, the solution will be reduced only in complementary function. Okay, the solution will be only the complementary function, like this. So this is the complementary function, because pi here is 0, because there, okay, it is equal to 0, it's homogeneous. Then here you have just to multiply by C1 plus C2. Because we said this is a one solution, this is second solution. So this is one solution and second solution. So the value of arbitrary, how can I say? The number of arbitrary constant will indicate how many solutions do we have, or how is the degree, or how is the order of this differential equation. Okay? So as the order of the differential equation is 2, so it must have 2 arbitrary constants. Okay? Now you are done. So what does it mean? Okay, in general way. It means that in general way, whenever we have, okay, like as you can see, this is case 1. This is when you have 2 roots or more roots that are different to each other. As you can see, v is equal to -1, v is equal to -5. When we have 2 roots that are different to each other, it means that, okay, 2 roots that are different from each other. 2 roots different each other, it means that the general solution will be, okay, will be equal to Euler raised to m1 times x times c1 plus Euler raised to m2. m2 is the second root, okay, okay, times x plus, okay, plus, okay, infinite sum of what? Of cn Euler raised to m and x. Okay, just like this. This is when we have real, okay, this is the general solution for when we have real, okay, when we have real different, real different roots, okay? These roots are real, and these roots are also different. So this will be the general solution for this homogeneous differential equation. Nice? Now let us jump to another one. Okay? Now let us see what will be the general case for this case too. Okay? Just remember, here we got the general case just from one case. The general case is that. Okay? Suppose it were something like v is equal to -1, v is equal to -5, v is equal to -6, -7, -8, -9. So you should just add, okay, for m1. m1 is the root, okay? M is the root, okay? Where m is the root. And c, we know it is like, yeah, this one. Okay, sorry, I was forgetting something here. This is time c2, okay? Plus, okay, 3 point, and this guy. Nice? Okay.